around the world. So this is the second seminar of this series. The first one was from Hiroshi Amano, and then we will have other like Omar Yaghi, Silvia Picozzi, and we end up with a Nobel Prize Bernard Feringa. Una comunicazione di servizio per gli studenti che vogliono avere riconosciuta la partecipazione a questo seminario. Dovete venire a firmare il foglio presenze alla fine, lo metto là in fondo sulla destra, prima di uscire venite a firmare il foglio presenze. So, please, Professor Pacchioni.
Long. No, it's a great pleasure to have Georg here with us. It took a while before to convince him, but finally we succeeded. And usually you say the speaker doesn't need an introduction. This is really a case. He is very famous because he is the main author of a very popular code for electronic structure theory, which is the code VASP, and which is been extremely successful. And in fact, I think the papers reporting the fundamentals of this code have been cited 100,000 times. But Georg, he studied physics in Wien, and then he did a postdoc with Jürgen Hafner, basically. And then he moved to UK, where he did a postdoc with Mike Gillen. And he also got an offer for a chair in Oxford, but he decided to go back to Wien. And since 2007, he is a professor in computational quantum mechanics in Wien. And of course, he got many important prizes, like the Hellman Prize, the Cardinal Initzer Prize, and recently an honorary degree from the University of Lund. Well, of course, as I said, he is very well known for the code, but he has given many important contributions to our field, both in terms of development, method developments, but also in terms of applications. And for a while, he was working in the same area where I've been working, oxide surfaces and oxide thin films. And for instance, I remember every time Georg was attacking a problem, he was solving it. And, like for instance, just one case, there was a long-standing controversy about the structure of the alumina, ultra-thin films of nickel aluminum, and finally this was solved by a collaboration between Georg and there was Peter Varga, I think, and Michael Schmidt, that was published in Science. But that was finally the solution to a complex structure which has been divided the community for several years. But it's just one example. So today is talking about the future of our field, which is machine learning and beyond DFT. And so we are very looking forward to your lecture. Please.
Yes, first of all, I want to thank Gianfranco and all of you for inviting me to give this talk here and to have the opportunity to talk about my research in the last few years. This is mostly an overview talk, so I will not present too many details, but rather try to give you a bird's eye view, what I believe is the future, or what are the pathways towards more accurate and more efficient calculations. I will also point out caveats or things and issues where we have a kind of still problems with, say, density functional theory and ways to kind of reduce those problems. So, introduction, I will talk a little bit about many-body physics and the specifics of density functional theory. I will give you an overview of machine learning and detailing how we do it in Vienna within the VASP code. I will then talk about something that was at the heart of my research for almost 10 years. That's the so-called random phase approximation. And I will demonstrate you how the combination of machine learning and beyond DFT methods actually allows you to do calculate finite temperature properties on the level of the random phase approximation for a variety of properties. And then I will give you a glimpse on what we are currently working on to go beyond density functional theory. That's called auxiliary field quantum Monte Carlo. I don't know how much time I will have, but I will give you a feeling where we are heading in terms of higher accuracy, so going beyond density functional theory, because ultimately I believe this is necessary to make modeling really quantitative. I will finish with some summary and conclusion. I think there's no need to introduce to chemists or physicists the Schrödinger equation. And we all know that we want to deal with atoms and electrons. Specifically, electrons are the glue that essentially hold our world together, right? We know that, and in order actually to describe electrons, you really have to rely on the Schrödinger equation. This is the monibody Schrödinger equation, and it rests on the inside of many scientists doing basic research between 1910 and about late 1960. There have been probably 10 to 20 Nobel Prizes in this area that we often do forget. This is a picture of Feynman, as far as I remember. So here's again the many-body Schrödinger equation, just to highlight what the issue is. The number of coordinates in the Hamiltonian, in fact, depends linearly on the number of electrons. So the number of coordinates you have in this object is proportional to n, the number of electrons. So you have a kinetic energy operator that's the Laplacian that operates on each coordinate. We usually treat the ions as classical particles, so they create a field or a potential in which the electrons move. Again, this acts on each electronic coordinate. And then there's one term that creates all the problems, if you want so, in solving the Schrödinger equation. That's a two-electron term, as it is called. It's a kind of repulsive term between any two coordinates. So what are these coordinates? Well, they are actually the coordinates in the object that is called wave function. And again, the number of coordinates we have is actually proportional to the number of electrons. The point here is this is a really simple object, right? So it's a linear partial differential equation. So it's really about the simplest mathematical objects that one can think of. And if you want to accept for relativistic effects, it describes, it's a kind of world formula for us, right? We all use it in essence. DFT is an approximation to it, but we can think of this equation to be our basic founding equation of quantum mechanics, and that's what we still use and would like to use today. The problem here is that the complexity in general is most likely, for the most general case, non-polynomial, so it's a non-polynomial hard problem. That means if you include more electrons, the compute time, say, becomes 10 times larger. So whenever you add one more electron, you need 10 times more compute time to solve the equation exactly. And that's why actually supercomputers help, but they don't help a lot because, yes, the compute time actually increases by a factor 10 every couple of years, but it just means if you solve the exact Schrödinger equation, you would start with 2 electrons in 2086 and today be around, say, 6 or 7 electrons. Yeah. So just brute forwardly solving this equation is simply not possible. And I think we have to accept that, right? Or we have to rely on approximations to actually do useful things. Even storing this quantity, this wave function that depends on many coordinates, is actually exponentially hard. So whenever we add one more coordinate, in a naive manner at least, the storage that we need actually increases by, say, factor 1000. And of course, we want to deal with hundreds of electrons in molecules, say in pharmacy, in catalysis and material science. We face very complex properties that require materials with often hundreds of atoms in the unit cell. So we must be smart. Just relying on faster computers will not ever help. I'm quite honest. I think ultimately this challenge is probably unsolvable to us, which is nice. So God has kind of given us a hurdle that we can possibly not really transgress, right? There's not probably a way to predict exactly what this equation predicts. Okay, our favorite theory nowadays is density function theory. This is Walter Kohn. And how do you think about density function theory? In the true many-body picture, you have a wave function, say, of 5 coordinates. These are the positions of the electrons. And you need to have an object that depends on these 5 coordinates. And in density function theory, the conjecture is, or it has been proven, that everything depends on the density only. So you kind of have a mean field object, a statistical object, or a mean field object that requires, it's just a one-dimensional function that describes how likely it is to find an electron at a specific point in space. And that's a much simpler object. The problem, however, is that the exact density functional is unknown, and we don't know exactly how the energy depends on the electron density. We have just approximations. To be honest, I have doubts that it can be ever found, this exact functional, and even if it would be found, it would be probably too expensive to be evaluated routinely. So I think on the long run, we will fall back to solutions of the true many-body Schrödinger equations, approximate solutions. And I think this is the only way forward on the long run. So here's a picture I tried to draw, kind of to convince you that it's not so easy to deal with density functional theory. So in density functional theory, say you have two nuclei, and this is the electronic crowd. So whenever there's a little dot, it meets the probability, there's a probability to find an electron. Let's imagine there are two electrons moving around. The problem here is the following one. The wave function observes certain principles. So if there is a high amplitude to find one electron here, we know, because of Pauli's exclusion principle, that the other electron is on the other side, right? We kind of really know that. And if actually this electron here moves over here, to be precise, if there's a high probability to find an electron at this position, then there is a high probability to find the other electron on the other side. And these electrons will always move in a concerted fashion. So if the electron now moves over to the other side from the left to the right, then the other electron will move to the right. And think about knowledge of the density only. Okay, imagine that you know only the density. Then this correlated movement intrinsically cannot be described, right? You just look at the average density here and here. It doesn't contain any of these fundamental correlation effects. And this tells you there is something really strongly approximate in density functional theory that we have to be aware. So I think this provocative thing here tells you that it's not so easy to find functionals that will perfectly work for every single case. Okay, let's make no mistake, one electron theory by construction have really faced difficulties to describe that situation. Yes, we know that Walter Kohn has proven that it is possible in principle, but the functionals are just very complicated. And here's a kind of a second view on the subject. It's the predicted adsorption energy for different functionals for benzene on different metal surfaces. Here's the experimental value, and here is the value that we predict using a theory that is called random phase approximation. I will give you a few words on this in a second. And what you see is this agrees very nicely with experiment. I mean, I think the precision is acceptable. And if you look at different theories, for instance, for the adsorption of benzene on palladium, you predict very wildly different numbers using different functions. That's why most users of density functional theory use different functions, many functionals, and then pick the one that they believe will correspond best to experiment. And currently there's really nothing to avoid that step, right? We have to screen functions in order to pick the best. Here is another way to compare it. This is adsorption of benzene on different metal surfaces, copper to rhodium, for a specific functional. This is PBE, Tanchenkov-Scheffler. And yes, that's not so bad compared to experiment, but there are outliers like this one here or that one that just don't compare very well with experiment. Probably nickel is probably the worst because I think this value predicted by RPA is pretty precise. So this is the state. Here's another view on this, and I will come back later to this. This is actually the temperature isobars. So this is the temperature and the density of water, respectively ice. And you all know that, no, I'm not allowed to move away. You should all know that there is a density maximum around roughly 278 Kelvin. So water has its highest density at 278 Kelvin. A few Celsius, I think 4 Celsius above zero. It's very important, right? Because water sinks to the bottom of the oceans, right? And the bottom of the seas. And ice actually is on top, right? And if this wouldn't be the case, our world would be very different, right? So it's really an important property to predict. This is the experimental isobar with this maximum here shown roughly, of course, at the right place. And look at what density functional theory predicts for all these different functionals. So there's a slew of functionals that we have explored, and it's fair to say that none of them actually provide a good description of liquid water, right? Some are actually dreadful, like these ones here, PBE0 plus D3, just doesn't work at all. What happens if you use actually these functionals to describe electrolysis, electrocatalysis? I don't want to know, but it's certainly a very approximate way to treat water if you use any of these functions that don't even get you the density function. Okay, anyway, all this data have been obtained by a combination of first principle calculations and machine learning. And machine learning, this is here the first important takeaway, are now able to bridge this gap and to do these calculations in, say, roughly a couple of weeks, maybe a month. So something previously was not accessible. So density isobars of that level of accuracy, I think, for water have not been published before. There are some for some functions, but doing a lot of these functions is only possible nowadays with machine learning. Furthermore, machine learning, and I will try to convince you of this, are a way forward because you can use them to learn the difference between a low-level method, say DFT, and a high-level method, such as the random phase approximation, and by means of this, go beyond density functional theory. So high-level methods are becoming progressively accessible if you actually use machine learning. So wrap up one, we need methods beyond DFT, as I've shown you. Large spread of of data for different functionals. Also here, no nice agreement with experiment yet. I firmly believe that DFT will never get to the point where it becomes truly predictive. Does this matter? Well, we all know in many cases it does not matter. Yeah? You can just try to figure out the best functional, and there's always one functional that gets you kind of the right result. But this requires expert knowledge, and I know there are a lot of people here in Milan that do a great job in selecting the best functional, right? You usually have a kind of, after years of expertise, you know which function to choose, but I think this is really unpleasant because it requires expert knowledge. The literature is full of this, so maybe we can rely on AI to figure out which function works best for which material class. However, looking in the not too distant future, we certainly need methods beyond DFT. And I think machine learning is kind of an enabler in this respect. So what kind of machine learning do we do in WASP? We rely on something that is very similar to the approaches by Gabor-Chani that are commonly referred to as SOAP gap. So our approach is very much in that kind of line of thought. It's certainly not a state-of-the-art functional, but that has advantages and disadvantages. The advantage being that it's actually very fast, the disadvantage being that it's actually not the most accurate approach available. So how does it work? Consider a central atom, the blue atom here or the red atom here. Essentially, you assume that the energy of this atom, the local energy of this atom, is dependent on the environment around this atom, respectively this atom. And you categorize your environment by two ingredients. That's the likelihood to find another atom at a certain distance. It's kind of the pair correlation function. So you kind of determine the pair correlation function around the central atom here and here. And that gives you a fingerprint. And you assume that your energy is linearly dependent on this fingerprint. So the pair correlation function is the first input. And the second input is a three-body correlation function. That's the likelihood to find one atom at the distance s, another atom at the distance r, and the likelihood to have a certain angle between these two second nearest or between these two neighbors. So it's a three-body correlation function, essentially the angular distribution function. So in these methods, you assume essentially that your energy, your local energy of the central atom is only dependent on the pair distribution of all the other atoms around it and the three-body distribution function of all the other atoms around it. That's essentially all that you need. Now, the nice thing about these two descriptors are that they are rotationally invariant. So if you rotate your entire system, these properties, the pair distribution function from the central atom and the three-body distribution function from the central atom's point of view remains completely unchanged. So your energy is also invariant under rotations. The second ingredient we use is actually a kernel-based approach. And I will kind of give you an idea what the kernel-based approach is. It's very simple to comprehend. Imagine you have different structures X, categorized by, say, in this case, a simple scalar variable. And you have an observable, say, the energy. Say this is the curve, the original curve that you have, and you have some data points. And in the kernel method, you do an almost trivial thing. You place at each of these points here a Gaussian, and then you adjust the Gaussian, the height of the Gaussian, such that you reproduce best as possible the original data points. That's all you do. So it's a kind of basis set approach where you place Gaussians at certain positions and adjust the height of the Gaussian to fit your data. That's all that there is in kernel-based methods. Usually the function that you place there is kind of variable, so you can choose different functions, but most of the time one uses an exponential function, but you can also use such kind of polynomial function that is centered at this point. That's also possible, and we do that, in fact. That's a suggestion by Gabo Chani that we have adopted from his work. But it doesn't matter, you could use a Gaussian as well. It's just computationally a little bit more efficient to use this. So you have a one-dimensional descriptor. Of course, you have in reality higher dimensional descriptors. You place Gaussian there and you adjust the height of these Gaussians to fit your original data as best as possible. This is essentially a kernel-based approach, very similar to SOAP-GAP. The second ingredient, and that's a little bit novel, is that we do uncertainty predictions using Bayesian regression. That is, we not only predict the energies and forces for new configurations, we also predict how accurate these predictions are. So we predict the variance of the predictions, so essentially the uncertainty of that prediction. And it turns out that this uncertainty, the predicted error, that's the red curve, correlates very nicely with the true evaluated error, that's the black curve. And you see whenever there's a spike in the true error, then actually we have also a spike in the predicted error. Here also the error goes up, the predicted error, and that also aligns with an increase of the actually real error. So that means our predicted error is a measure of how good our prediction is, and if the prediction is not good, we need a first principles calculation, and that's what the VASP course does. So if the prediction error is large, we actually perform a first principle simulation, and we actually retrain on the fly our machine learned force field. And that means progressively our force field becomes more accurate. At the end, we don't use Bayesian regression. At the end, we use actually, when we do solve the fitting problem, the one I was talking about before, we use essentially an SVD, singular value decomposition, because at the end of the day, this is the best way to solve a regression problem. So if you have a regression problem of that kind, that's the solution using Bayesian regression. But at the end, we usually resort to calculating the pseudo-inverse of this, and then this gives you these weights. The weights I put at the Gaussians initially, and this is about a factor 2 to 3 more accurate than what we used originally. Okay, how good is this? Here's a comparison for different systems: water, liquid sodium chloride, absorption of CO on rhodium, cesium, lead, bromide, and for different molecules. These are errors in forces given in millielectron volt per angstrom. The first thing you see, errors for molecules are generally quite small, and errors for solids are generally quite large, in particular for such systems such as CO adsorption rhodium. I can explain you why this is so. Essentially, it has to do with the fact that rhodium is a dense metal with a lot of neighbors, so only using 3 body functions is not good enough. That's one reason. But also in solids, we have long-range interactions, right? In a molecule, in a small molecule, and this is what these test sets are about, you have no long-range interactions. So if you use a finite cutoff, I was previously drawing a sphere, you are perfectly fine. In all these systems, you do have long-range electrostatic interactions here, for instance, here as well, and here as well. And here it's mostly metallic behavior, which includes, causes long-range Friedel oscillations that we can't capture. What you also see is we compare here with a recent, quite state-of-the-art short-range model that's called ACE. You see that the VASP results are pretty much on par. For molecules, we are about a factor 2 worse than ACE, but otherwise, I think the performance of VASP is respectable. And the timings we measured was also pretty much similar between ACE and VASP. So typically here are some timings, I will not read it up. And these timings imply that your calculations become typically between a factor 10,000 to 1,000 more faster than the original VASP calculation. That's immense, right? 10,000 means 20 years of computer developments. It translates to a 20-year time span for computer developments. So this really enables a new kind of computational protocol for the future. I give you one quick example that I think would have been completely impossible. We tried it with first principles before machine learning became available. We tried to predict phase transitions in methylammonium. Methylammonium is this little molecule that's actually encaged in lead iodine. That's a perovskite. This molecule rattles and moves around in this cage. When I first tried this, around 100,000 time-step MD calculations somewhere in this regime, and I could not tell anything. Yeah? 2 by 2 unit cell, I could not figure out that this was tetragonal on average, just completely impossible to get any insight. With machine learning, we can now even predict the phase transition boundaries between the orthorhombic structure, the tetragonal structure, and the cubic structure. Here's the second order, here's the first order phase transition, here's the second order phase transition in our simulations. And comparison with the experiment is very nice. So in order to do this, we just learned on the fly. So we just heated methylammonium lead iodine 3 from, I think, 200 Kelvin to about 400 Kelvin. That's all what we did. And then we used the machine learned force field to predict the phase diagram of this methylammonium lead iodine 3. On passing, I want to mention, this is the first calculation. A student of mine redid it, and these are the current simulations, which you see are much better. Yes, there's progress. After 5 years, we can actually do more accurate simulations. We can be more patient to create the force field. It seems like the dominant error here was actually that our force field was not quite yet good enough. Now the phase transition boundaries would much better align with the experiment. You might ask which functional? This was scan, okay? Actually, you wouldn't get anything useful probably with PBE and PBE-D3 in this specific case. Well, we tested before. Scan matches very closely with RPA. There's another paper we published before, and that showed that scan and RPA closely match. So scan is the best functional for this case. So are the machine learning potentials in VASP good? Astounding in terms of performance there are, as good as it gets. So we have a GPU board, we have a LAMPS interface up and running, so you can also use LAMPS after fitting. In terms of accuracy, they are good, but not exceptional. So there are better and more accurate approaches. Particularly, I want to emphasize any message passing neural network like NetQuip, Maze, or Grace beats us in terms of precision, in terms of errors by a factor 2 to 3, hands down, at least a factor 2 for solids. The problem with those are that you need GPUs. You cannot run any of these message passing networks. They are incredibly complex, and they only are so fast because NVIDIA and all these people have invested a huge amount of time to actually run these at peak performance, 40 teraflop for a single GPU. Only then, and even then they are 10 to 100 times slower than what we have in VASP. And in VASP you can run on the CPU, you don't need a GPU. And sorry, we don't have a lot of GPUs yet in Austria. I don't know how it is in Italy, but I think the situation is pretty similar since all the top buyers of NVIDIA GPUs are sitting in the US, right? So it's also easy to construct force fields, you just do this on the fly training. Okay. Now, the second thing I want to briefly mention is this random phase approximation, right? This is our favorite beyond DFT method and has been our favorite beyond DFT method. It's on the rung 5. If you read John Perdue's paper, he likes to write always, it's not any better than scan. Okay, he always writes that irrevertibly, almost in defense, right? And I agree with him, it's probably not much better than scan, and I will show you some evidence of that. But it's much less kind of empirical. So what is it? We take photos thoroughly. I thank, of course, the Austrian Science Foundation, in particular Taco, Max, and the Auxiliary Field Quantum Monte Carlo, and you for listening. Thank you so much.
Thank you, Georg, very much for this excursion in the future of our field. And well, now the paper is open for discussion and questions. Okay.
So thank you, Georg. One question is this delta learning. You are claiming, 10 calculations might be sufficient to get a good description of the correction. What is this telling us? I mean, there must be some general reason for that. Like maybe it's possible to derive an approximation, an analytical model. I mean, 10 is really a small number. It's so close to be a shift.
Yes,
I mean,
but 10 is deceptive because for all these 10 calculations, we have 64 atoms. no, 64, no, I'm thinking was 64 molecules times 3, so each of these calculations had 192 times 3 forces, so 600 forces.
Okay.
600 forces times 10, 6,400 data points.
Okay, that's more reasonable. Thank you.
Yeah, it's not so small, right?
Okay,
It's deceptive.
Okay, thank you.
Without forces, you need at least 1,000 energy calculations.
Hi, thank you for your nice talk. Similar to that question, but correlated. How can you be so sure that the difference between high and low level is so simpler than, I don't know, from scratch predicting values?
I mean, these are test set errors. The errors are documented for water are from test sets, so that we train on 20 structures, we have a test set. I think the test set was even, if I remember correctly, it doesn't matter, but the test set was not overlapping with the training set. It was still taken from trajectories of water, but it was completely independent from the training set. So it's an unbiased error estimation. Unbiased is a little bit too strong. I mean, it's the best you can easily do, yeah? So an error of 2.5 millielectron volt per angstrom is really, really tiny, yeah, for a completely independent test set error. Of course, you have to evaluate this. I mean, for CO and rhodium, the errors were, for instance, much larger. Yeah, it's much more complicated system, and there's much more difference, of course, between DFT and RPA, right? Because DFT predicts hollow side adsorption, whereas RPA predicts top side adsorption. So this is harder to learn, yes. Yeah, you have to do tests. Without tests, you cannot. Unfortunately, for the RPA, tests are very expensive because every single test takes you, 2, 3, 4 hours and 4 nodes, which is expensive.
So, any more questions? Yeah.
My question regards the last part of your talk when you were talking about stochastic methods.
Yes.
How can you be sure that the ground state is unique? So you say that the trial wave function must be non-orthogonal, otherwise you end up in the wrong Hilbert space?
Yeah, I mean, let's be clear, for instance, for metals and for a lot of systems, there can be, of course, problems. Metals and strongly correlated systems are clearly still a problem because you might not even overlap. Your trial wave function might not overlap. Actually, this is already one of the reasons for the remaining issues we have here. If you look at those, if you look here, we have some molecules that do not work, right? And there the overlap between the trial wave function, the Hartree-Fock wave function, even the Hartree-Fock wave function, and the true ground state is much smaller than for the other ones. You see this already in a cusp calculation, that here the Hartree-Fock is not a good surrogate. We also know now already why we do not improve here. Well, the point is that we draw these additional determinants from an approximate Monte Carlo procedure, and I think this is the reason why we have this error. I think we can cope with this on the long run, but that needs more research work. But yes, you are completely right. You have to be very careful in the selection of your trial wave function.
There's a question here.
Hi, it's a fantastic talk. I have 2 questions. The first one is in the slide number 13, when you were talking about the kernel method. So I'm not sure, I mean, maybe I missed something. So you talked that it was something like initially it was in one coordinate and then you map it in higher dimension, right?
Well,
so,
yes, I was very, very brief on this. This is what I call a moniker, so it's not truly what we do, of course, or what any kernel method does. A kernel method, of course, this is a showcase of a one-dimensional method. When we use it, or when anyone else uses a kernel method, you work in high-dimensional space, but most of the time one uses the so-called radial basis function, which is a multi-dimensional Gaussian function, where you measure the distance from your point, using what is called this exponential, I would call it the Gaussian function. Mathematicians, machine learners call it the radial kernel function for whatever reason. But it's multidimensional Gaussian. Yeah. I mean, chemists know that probably what a Gaussian is, right? Yeah.
Okay, yeah. So that was my question. Like
it's always a multidimensional Gaussian, but for this example here, to kind of give the most easiest way of understanding it, you can also do it in 1D, of course.
Okay, yeah, thank you.
In practice, you can never do it in 1D. You always have to do it in multidimensional space. This is just a moniker.
Mm-hmm. Okay, and like the other one is when, I mean, maybe it's in the next slide, when you were talking about this Bayesian regression. So just one question, like, I mean, Bayesian, when, I mean, we are using it when we have some uncertainty in predicting something, right? So here I'm not sure, I mean, why we are using this Bayesian regression here, maybe. So
why
I didn't understand this.
Yeah,
like this one.
Yeah, here there are also no equations. The advantage of the Bayesian framework is that you get an uncertainty prediction. If you use straightforward kernel methods, which you can also do, you don't usually get an uncertainty estimate. You can kind of bring it back into your equations, but that's not the natural way of doing it. The Bayesian regression gives you natively an uncertainty estimate, and that's why we use Bayesian regression. So it natively tells you the force error, or the uncertainty of the error of the force prediction and the energy prediction. So you have a covariance matrix, and from the covariance matrix you get a precise prediction. You get an uncertainty estimate, and that's only available in Bayesian regression.
Very good. So, any more questions or curiosity? Well, if it's not the case, well, we thank Georg again for this fantastic talk. Thanks for coming. Many of you are not from our university, so we appreciate it.
Yes, thanks all for coming. I know I was, as always, talking too long. I'm sorry for that.